Alright, this is my fourth attempt or something like that to record this video. I've been interrupted a few times. Let's see if there's going to be a fifth attempt. Anyway, so my attempt here, what I'm trying to do is to demonstrate how to implement a native function in CAP, a function that is implemented in Kotlin itself. So I prepared a little bit by creating an empty module, and a module is simply a way to encapsulate CAP functionality, so I can easily remove and add it, and you can actually also extract it into separate files and load them independently of the interpreter. So using a module for this is quite nice because it allows us to put all the code we need for this particular example in a single file, which we called simply called demo module. Or to be 100% accurate, the file is called demomod.kt. So what we'll do is, the first thing we have to do in the initialization of the module is that we have to give our function a name. And names in CAP are symbols. And symbols live in namespaces, so the first thing we have to do is we have to create the namespace, or find the namespace if it already exists. So that is called make namespace, and it takes an argument called, let's call it demo in this case. And the function we'll create is a simple function that will do nothing but swap the first two elements of an array if it contains two or more elements. And otherwise it just returns the element itself. So what we can do, we take the engine, which is the main entry point into the interpreter, and we register a function. And the name is we call intern and export of, and let's call the function swap, and then it needs an implementation of the actual function. Call it swap function, like that. And the swap function has to be an implementation of APL function descriptor. So let's implement that. APL function descriptor, and swap function inherits from APL function descriptor, like that. And we have to implement some members. It's an interface, you don't have that. All the APL function descriptor specifies is a function called make. And what happens is that you register a function descriptor in the engine itself. Here at the registration. So when the parser then sees a call to a function, is called case function swap, it will then call make to instantiate that function at a specific place in the code. And it does that with a function instantiation object, and the function instantiation contains a position, which is the position in the source code where the instantiation happened. So this is the position is passed along in a lot of functions because you have to know it tracks the location where the function was used, so that error messages can point to the correct place. In most cases, there's not much to worry about. You just have to pass the appropriate position along with whatever operation you want to perform that needs a position. Anything that can throw an error can then needs a position. The environment contains information about the local call site, like the lexical variables and things like that. So an advanced function can do things with that. So let's take a look at this. So when a function is instantiated, then we will create an instance of an APL function. So what we'll do here is return, and it is called swap function impl, and it will just take the instantiation as an argument. And let's just declare it. Normally, I just declare it inside the enclosing function descriptor, because there's almost always a dedicated APL function associated with each descriptor, and you normally never instantiate the APL this function separately from the descriptor. So putting it inside makes sense. Swap function impl, and it implements its subclasses APL function, and let us do that, and the instantiation is passed along there. Okay, so an APL function, and actually an APL function is quite complex. It has a lot of open methods, which means that they can be subclassed by functions that want to do advanced stuff. However, in this particular case, it's a very simple function. We don't have to worry about any of this. All we have to do is subclass implement a single method, which is called eval1arg, because it's a monadic call. And even better, since this function doesn't use an access parameter, we can use a subclass of this called noAccess APL function. And what this does is simply provide some default implementations for the function calls, and if it passes an access, it will just raise an error. So what we can do now is we can implement this guy here, and this function will then be called when this function is called monadically. So if you do eval2arg, you will get the same similar function signature, but there are two arguments. There's an A and a B. So what do we do? Well, the first thing we want to do is we want to take the dimensions of the argument. This is the shape, basically. And if it contains two or more elements, we want to return a lazy object that represents the swapped result. And if it doesn't, if it only contains one, if it's a scalar or only contains one or zero elements, we just want to return the object itself. So we will return if the dot content size, which is the number of elements in the array, or which should be greater than or equal to 2. And if that is the case, we will then return a swapped value like that. Else we will simply return A. So what does swapped value look like? Well, swapped value is has to be an implementation of APL value. APL value is just the class or that represents any value in the interpreter. But what we'll do here is actually we'll subclass a specific subclass of APL value called APL array, because this is APL value can represent both arrays and atoms, and here we want to deal with an array, and this guy here gives you a lot of default implementations, so you don't need much. You don't need to add much else. So what we do here is this, and it takes and we implement the members, and as we can see, we only need to implement two methods. So dimensions, the dimensions is just we can do this. It's just the dimensions is literally just the dimensions of the parent, because of the original class, because obviously swapping two elements doesn't change its shape at all. And value at simply returns, this is the an int, which is the raveled index into the array. So as if you run the monadic comma function on the argument, you get a single dimensional array, and whatever index into an element, whatever the index to an element is, that is p in this case. So all we have to do is we want to do when p new index, when p is 0 we return 1, when it's 1 we return 0, else we return p, and then we simply return a dot value at new index. And that should be it. I hope this works. I haven't tested this, so let's run it and see what happens. Now we have to wait for it to compile, but with a bit of luck this will swap the two first values in the array. While this compiles, maybe I will just mention something about error handling. We can take a look at what no-access APL function does, because if we can see here that if you call the function with an axis, what this specialization does is that it just ensures that access is null and raises an error if it's not. And what does it look like? Well, it's as simple as this. So it just checks if access is not null, which means that an access has been passed to the function. It will call this, and this is what I wanted to highlight. Throw APL exception. When an exception is thrown, an error is thrown from an APL function, and that error represents usually user error, and you wanted to display it as a normal error by the user. You want to use the function throw APL exception. This will eventually throw the actual exception, but it does things like filling in the stack trace and things like that, which is why it's important to use this and not just throw. So if you take a look at this implementation, you see it gets the current stack frame, fills that into the exception, and then throws the real exception. Alright, so let's go back to our code and look at the implementation, and let's do 10, 11, 12 and demo swap, and it seemed to work. So iota 10, and if I just have a scalar or a single value, it works. So that's it. I hope this helps someone that might be interested in actually implementing something in the CAP interpreter, and well, if not, I hope it's entertaining anyway. Thank you, and bye.